Yeah, I know. That's what it's supposed to do. There. Okay. So you should have this paper here. There are some portions in the notes that relate to, on your regular notes that I gave you guys before, that relate to empirical formula and molecular formula. And I have actually a recording on those, but there's not really, I don't have a ton of stuff in the notes. And as I looked through it, I thought this actually does a little bit better job of sort of systematically laying out what we're doing with empirical formula. We've done percent by mass, right? Percent composition by mass. And this is sort of the next step on that. Because you can do empirical formulas if you have the percentages, or if you have the masses of each of the items in there, you can do empirical formula as well. So let's start by taking a look at and start filling this out for you. So the empirical formula, the reason why it has a weird name, empirical formula, is that it's not really necessarily the actual formula for the substance we're talking about. What it ends up being is the lowest whole number ratio. So this is, I got to do this. I'm going to push this up a little bit. I'm going to do that. And I'm going to do that. So this is the lowest whole number ratio. So when you look at a formula, let's say the formula is C4H10O2. This is just a ratio, right? This is telling you that if I have 4 carbons, I'm going to need 2 oxygens. If I have 10 hydrogens, I'm going to need 4 carbons. Like that tells you the ratio of those things between each other. So we can figure out what that ratio is actually fairly easily with just a little bit of math. The molecular formula is where we're going to come around to that too, sort of tack that onto the end. The molecular formula is the actual formula, okay? So this is a ratio that may or may not be the actual formula, but actually has the right ratio. The molecular formula is the actual one. Now, there's a reason why we call this molecular, and it doesn't include formula units, and that is when we have an ionic compound, it's in the lowest ratio already that we can make it, right? It's already got to be. So if we have sodium and chlorine, we're going to have 1 sodium and 2 chlorines, right? It's going to be sodium chloride is going to be NaCl2 automatically. That's the lowest ratio that we can do. So all ionic compounds technically are already the empirical formulas. So all of them are all going to be in that format. The only ones we're going to be talking about here are going to be covalent compounds where you might have this. This might be the ratio we came up with. Your actual compound might be C16H40O8. Does that make sense? That's the same ratio, right? But this is an entirely different compound. And there's lots of examples of compounds that have the same empirical formula but have different molecular formulas. And one of them, we're going to look at one. Like one of them might be used as a medicine and another one might be used as an explosive. And they're almost identical. They have the same proportions, but there's different sizes. Okay? So let's look here. I'll give you an example here. A molecular formula might be C6H6, and an empirical formula might be CH. Okay? So see how that works? It's the same proportions, but this is the actual formula, and that would be the empirical formula. The empirical formula just gives you the actual ratio of them. Okay? And I'll show you, once we find an empirical formula, it's super easy to find the molecular formula. Okay? If you have the right information. If you don't have the information, it's impossible. Okay? So I like to put on here that this is like actual, and this is a ratio, right? This is just the ratio of the two to each other. They bring up ionic compounds here, formulas for ionic compounds, called formula units, right? They are always empirical. Because you can't have, we saw before, right? You can't have, so NaCl2, you can't have a formula that's Na2Cl4, right? That's not valid. Doesn't work. So ionic compounds are always in the empirical formula. They're never like this. The only ones that are like that will be the covalent ones. That's why we have to have the prefixes for covalent compounds, right? Because we have to tell you what's in there, because it could be pretty much anything. The empirical part here is that they're in the simplest whole number ratio. People of my generation, that was a number sign. People in your generation, I guess, is a pound sign? Or is that, what is it? What do you call it now? Hashtag. This is the old one. This isn't a hashtag. Hashtag ratio. No, that's the number sign. So, all right. So formulas for some compounds, so formulas for some covalent compounds could be empirical. So some of these might be empirical, but they don't have to be. So some of them may be empirical, but they don't have to be empirical. So I'm going to give you some examples here on this chart. I think I should raise this up. Are you guys all caught up with me here? Everybody's good? I'm holding. She stay off her phone. She'd be with us, right? What? I should start allowing other students to just take phones that they see and hold on to them for the rest of the hour.
It's actually invasion.
Okay. All right. Okay, here's some examples I want to give you. So if I gave you H2O, back that up so it looks better, H2O, the empirical formula for H2O would also be H2O, right? That's the lowest whole number ratio of that compound, H2O. What if I gave you C6H22O11? C6H22O11, that, again, I can't divide that by anything, right? I can't divide everything by something there. So it's going to be, again, it's C6H22O11. But I could also do something that's like N8Cl4 let's do O10. Then the empirical formula of that is going to be N4Cl2O5. Good. Okay. So you guys are catching right on. Have you done these before? Probably not. Oh, yeah. You have? Where'd you do them? At home?
Logic.
Gotcha. Okay. Formulas for some molecular compounds may have the same empirical formula but be different. So here's an example. If you had C3H6 versus C2H4, they both have the same empirical formula, right? it's going to be, the empirical formula is going to be CH2, right? The difference, though, is this is called cyclopane, and this is called ethene, part of ethylene. Cyclopane is used as an anesthetic, put you to sleep when you're getting surgery or something. Ethylene ethene is a very popular chemical used in industry and incredibly explosive, very flammable. Two things that are very similar, have the exact same empirical formula, but completely different when you look at them from that point of view. Okay, so they could have the same empirical formula, but be very different. Okay. All right. I want to pull that up. Everybody's got this, right? No. Where? What? B. Very different. I wasn't going to put anything there, but I thought I should probably put something there. Very diff. Yeah, they're very. So these are completely different, right? Like we use these in healthcare all the time. This one, if you breathed it in, you probably would kill yourself. It's not a good idea. Okay. So I want to give you the first part of this about how to do this is going to be giving you the logical way that you find the empirical formula, and then we'll sort of show you how it looks while it's being done. Okay? So the first thing you need to do is you have to figure out how many moles of each element you have. Okay? Everything comes back to moles. So determine the number of moles of each, and I'll show you exactly how to do that. If you're given a percent, you change it to this is a little trick that you do to make this work. If you're given percentages, just drop the percent sign and put grams on there and pretend like you have 100 grams of it instead of 100% of it. Does that make sense? It's like this little tool you can use to make this all, to get you to moles, okay? So if you're given a percent, change the percent to 100 grams and you're good to go. So each thing you have grams instead of percents. If you're given the mass, all you got to do is convert to moles, right? So both of these, you end up, if you're given a percent, you change it to mass and then convert it to moles. If you're given the mass, you just convert it to moles, okay? So all you're doing for that looks like this. You have a given mass. So I'm going to put it in grams over 1. You're going to have grams on the bottom, right? So this is going to be molar mass. And on top, you're going to have 1 mole. So in essence, you're going to take whatever your mass is, divide it by the molar mass, and that's going to tell you the number of moles that you have for each one of the elements. Okay? So that's how you're doing step 1 right there, is you're doing that formula. Then step 2, you divide each of the moles by the smallest one. Okay? This will make more sense after we walk through one. So whatever one has the smallest number of moles, you divide all the other ones by that. Okay? And then when you do that, you should come up with whole numbers. If you don't, you got to go to step 3. And if you don't, this is, you have to figure out figure out how to get all ratio numbers to integers. You got to get them all as whole numbers, okay? And I'll show you how that works. So if you get a set of ratios that looks like this, let's say you have 2 carbon, 1.5 hydrogen, and 1 oxygen, you can't come up with a formula that's C2H1.5O, right? That doesn't work. So how would you fix that? Multiply everything by 2, and now you've got C4H3O2. So, pretty cool. Okay. So let's do, I'll bring this up. We're going to do one of these here on this. Okay. So here it says that I have, this is not giving me a percentage. This is giving me the grams right off the bat, right? So it makes it easier. I got 1.72 grams of carbon, 0.29 grams of hydrogen, and 0.46 grams of oxygen. So I'm going to do this. First off, what I need to do is I need to figure out how many moles of each that I have, right? So here's what I'm going to do. I'm going to take 1.72 grams over 1 times, this is going to be 1 mole over, how many grams is carbon? 12 grams, right? Does that make sense? How I can figure that out? And when I do that math, I'm going to come up with 0.14 moles of carbon. Very small number, right?
Where'd you get the 12 grams from?
That's the molar mass of carbon up on the periodic table. Okay? So I'm going to do the next one is going to be hydrogen. So I'm going to go 0.29 grams of hydrogen over 1 times 1 mole. And I'm just going to say it's 1 gram, so that's going to equal 0.29 moles of hydrogen, right? Roughly? He said he was coming down and he'd be here as close as he could to that time, so he might be running behind. Let's wait a little bit more. Okay, so the last one is oxygen. It's 0.46 grams over 1 times 1 mole is 16 grams, right? That's going to come out to 0.29 moles of oxygen. Okay? You see where this is going?
Yep.
That's not right. 0 to 9. That a little better? Okay, now the next thing I'm going to do is go 0.14 divided by 0.029, 0.29 divided by 0.29, and 0.029 divided by 0.029. Do you see why I do those? I took the smallest one right there and divided each of those by that. That means oxygen is going to be 1. That means that hydrogen is going to be 10. And carbon is going to be, we're going to come up to about 4.9. So one of the things that you'll find when you're doing these is if you've never rounded anything before, this is the place where you will round in chemistry. Definitely. Because guess what? This is approximately 5 carbons. This is 10 hydrogens and 1 oxygen. What does that come out to be? C5H10O, right? See how I figured that out? That's your empirical formula.
Yes.
Okay? Figure that out, Andrea? Yeah.
Your
Sure.
one oxygen just looks like a 10%.
That's why I kind of put a dash in there. Oh, that one looks like a 10.
But it's fine.
Sorry. Okay. So it's not too bad, right? It's not the most horrible thing in the world. This is the reason, like, when you get worksheets of these, you'll have, like, 4 problems on them rather than have, like, 50 problems on them because they're a little bit larger to digest. All right. Let's look at the next page. So here's one where you're given percents. So again, percents on here are really, really easy. All you need to do is change this from percent to grams. So I'm going to do this. So part 1, I'm going to take 43.64 grams over 1 times, and this is phosphorus, which is 31. So 1 mole is 31 grams. Okay. The next one is 56.36 grams. I did not do that well. Over 1 times 1 mole over oxygen is 16 grams. See how we're trying to get, all we're trying to do is figure out how many moles of each of these we have. So we end up with a number that looks like this, 1.4. Man, I am not writing well today. Looks like gold. 1.4 moles of phosphorus and 3.5 moles of oxygen, right? So I'm going to divide by the 1.4 on there. So hang on. I'm going to divide by the 1.4. So I'm going to go 1.4 divided by 1.4. And down here I'm going to go 3.5 divided by 1.4, right? So I divided by the smaller one, which means that one's going to be 1, and the second one is going to be 2.5, right? Yes. So this gives me my ratio. So my ratio right now looks like this. P and then O. So then you have to multiply everything by 2. So I've got P2O5. Right? No problem. No problem. Okay. Everybody's got that? Everybody's good? All right. All of them. How many you think we should do?
No, together?
Do you want to do the last page yourself? That's fine. Okay. Yeah. You can do the last page yourself. Let's do the rest of this page, and then you'll do the last page yourself. Okay. And if you want help on the last page, just see me, and I'll help you with that. That's not a big deal. Okay, let's do this one here. 49.32 grams over 1 times 1 over 12 grams. And then we've got 6.85 grams over 1 times 1 over 1 grams over moles. And then the last one is 43.84 times 16 grams. Okay? Everybody with me so far? I just changed those to grams. Now when I do the math, this is 4.1. That's moles of carbon. This is that's 6.8 moles of hydrogen. And this one is 2.7 moles of oxygen. Okay? So now I got to divide, what's the smallest one? 2.7, right? So right away we know this is going to be 1, right? This divided by 2.7 is going to equal 2.5. And this divided by 2.7 is going to equal 1.5. So I've got 2 that I got a problem with, right? So I'm going to multiply them all by 2. So I got 3, 5, and 2, which means it's going to be C3H5O2. Okay? Now, I need to do one problem with you on the last page because we're doing molecular formula there. So I haven't shown you yet how to do the molecular formula. Okay, so that's how you get to the empirical formula. No big deal, right? All you're doing is figuring out you're figuring out the ratio of what makes up what on there. You're figuring out the mole ratio based on the gram or the mass ratio. Now, let me pull everybody okay if I pull this up? Y'all good? I don't want to get too far ahead of anybody. I'll wait for just a second. Actually, I'll fill this out here. So what if we know right here, see that CH2? The mass of that, okay, carbon is 12, hydrogen is 1, right? So the mass of that, forget about this, the mass of that's 14, right? Does that make sense? So the mass of that empirical formula is 14. So what happens if I go, C2H4, what's the mass of that going to be? 28, right? If I go C3H6, what's the mass of that going to be? 42 grams. I could go C4H8, the mass of that is 56. Ah, there he is. All right, cool. Okay. The question on here is, do you see a pattern? And that is that these are all going up by whole number intervals, and this is going up at the same exact rate, right? The mass and the formula all go up exactly the same each time, okay? All by whatever number it's multiplied by, okay? That's the key to being able to find the molecular formula from the empirical formula, okay? So, are we good here? Can I move it? Everybody's good? Okay. So, down here, here's the steps for getting the molecular formula. So we're assuming that you already got the empirical formula. And you go, okay, I need to determine the mass of the empirical formula. Okay, so I get the mass of the empirical formula. And then if they don't, like, you may be given a problem. This is just saying you may be given a problem where you have to calculate the empirical formula. Okay, if you're not given the empirical formula, you might have to figure it out, right? So you may have to calculate the EF, empirical formula. Okay. So now you have the mass of the empirical formula, right? The only way you can calculate the molecular formula is if you're given the mass of the molecular formula. You have to be given the molar mass of that. If you're not given the molar mass of that, and it asks you what's the molecular formula, you have to tell. Okay? So here's what you have to do is you have to take the molecular mass, right? That would have to be given to you. That's the only way you could get it. And you would divide that by the empirical mass. Right? You can figure out the empirical mass if you have or have figured out the empirical formula. Now you can just add up the empirical formula mass, but the only way to get the molecular mass is somebody gives that to you. Okay? So now what you come up with when you do this, you divide this by that, you come up with a multiplier. And we're going to call that N. For no other reason than it's a number. Doesn't matter. And you're going to use that to do this. N times N times the empirical formula. That equals the molecular formula. So if you get the empirical formula and then you find out that the molecular formula is 3 times bigger than the empirical formula, that's pretty easy, right? You just multiply everything by 3. Now you have the molecular formula. Okay? Make sense? So the molecular formula is like this little add-on thing. The empirical formula is probably the one that's a little more involved. None of it's like... the hardest part of this is that there's like 3 steps, right? There's a possibility of 3. When you're doing molecular formula, if you start off with percentages and you have to calculate the empirical formula, you might have 4 steps for one problem to figure it out. Okay? I'm going to pull this up. Hopefully we're ready. And I'm going to do at least this first one with you because here's, if you're lucky on a problem, they give you, like, see this right here? They give you the empirical formula. That's nice. You don't have to calculate it. So there's your empirical formula. And it says, here's the molecular formula mass right there. And it wants to know the molecular formula. So the first thing I got to figure out is what's the mass of that, right? So it's basically going to be 12 times 3 plus 1 times 5 plus 16 times 2. Do you see how I got that? These are the numbers in the formula right here, and these are the masses, the molar masses from the periodic table. Okay, so you've got what? 36, 5, and 32, right? Is that right? Yeah, that looks right. Find out if I did it right. Yep, 73. So this is 73 grams per mole of there. So that's the empirical formula. Now all I need to do is go 146.16 divided by 73 grams, right? What's that? That's cakewalk, right? It's 2, right? 73 times 2 is 146. Is that right?
Yeah.
Got it? All of this is going to be roughly on here. These are the least precise, probably, numbers that you're going to deal with in chemistry. 2. So what's the molecular formula? C6, H10, O4. No problem, right? Yeah. Peyton's like, give me a challenge. Whoops. I don't know why I put that line on there. Get rid of that. Let me double check and see if there's any real problems on here. Molecular formula of a compound has empirical formula. It gives you the empirical formula and the molecular mass. Determine the molecular formula for a compound. So here you're given the percentages. You got to figure out the empirical formula. Then you got to figure out the molar mass of the empirical formula. Then you got to divide it into the mass of the molecular formula, and then you find the molecular formula. So this is going to be like 5 steps. Okay. Down here, let's do this together, just because I think this can be tricky. So at the very end there, hopefully this will get you thinking about it a little bit. Is that right there? the molecular formula or the empirical formula, or is it both? So you got S2Cl2. Can you reduce that? Is it ionic? No. So it can be reduced. So it's not the empirical formula. So this has to be the molecular formula. Okay? What about the next one? Na2SO3. That is what? Empirical. Why? It is ionic. Yes. So because it's ionic, you always are going to be at that lowest common ratio. How about the next one, H2O? Is that molecular or empirical? It's empirical. Is it also molecular? It's both molecular and empirical. How about C6H10O4? That is molecular, right? You can definitely reduce that. So that is molecular. C12H17ON. It is empirical. Is it molecular?
Yeah.
It would also be molecular there. It's both of them. Sort of like water is, right? It's mainly if it is a covalent compound that is the empirical formula, it's also going to be a molecular formula. Okay? Both. Last one, NaCl. It's empirical. Because this is ionic, right? Can't be anything other than that. Okay? So the mixture of sodium and chlorine cannot take any other forms, right? It's just going to be NaCl all the time. All right. Over here, acetylene is C2H2. Benzene is C6H6. Do these compounds have the same empirical formula? Absolutely, right? Yes. What is that empirical formula? Oops. Yes, very good. CH is that empirical formula. Yes. Yes. Okay.